Okay, so so for today's course, we're gonna introduce the whiteboard distribution that can be evaluate the reliability of the bearing life of the roller or the ball bearings. Okay, so this is the distribution. Okay, whiteboard distribution. Okay, so how to get this variable distribution? Well, basically, it's a statistical method. We're not gonna focusing on it. So just briefly introduce how to get those data. Okay, so basically, we just run the experiment for different load cycle. Okay, so for example, when we have the that's just based on this data. So when we run the load cycles about 1041, we might get one sample fail. Okay, so when we run the load cycles reaching 2000 cycles, we got a two sample fail. Okay, so for this column, it's the cumulative fractured sample. Okay, it's cumulative fracture sample. Okay, so and so on. Okay, so we get the distribution of the cumulative fracture sample in with respect to the load cycle. Okay, the load cycle. So we can get each data point here. Okay, and if we counted the fracture samples, the individual fracture samples, we'll convert this cumulative fracture samples to individual fracture samples. Okay, so therefore we got it for this 2000 cycle, we got one. Okay, for these cycles, we got maybe three. Okay, for specific low cycles, we can get a different number of individual fracture sample. Okay. Okay. Similarly, we can convert this cumulative fracture samples into a probability. Okay, so right now the y-axis represents the probability. So it's the cumulative probability of fracture sample. Okay, and this is the probability of fracture sample. Okay, fracture sample. Okay, so it's the cumulative, this is the individual fracture sample. Okay, so and we define this distribution as the Weibull distribution. Okay, Weibull distribution. Okay. Okay, so if you still remember, we already learned this this plot log scale of the load versus life, right? It's the linear function, right? It's a linear function. Okay, so we can combine this two figures. First is the load and life plot and the Weibull distribution. Okay, so these two figures can be integrated. Okay, can be integrated. Okay, so when we get this Weibull distribution from experiment, so as we define the L10, what is L10? L10 is when these samples reach the 10% samples fail, right? Under, we say the load one, okay, the load one, specific load one, and we get the life of L10, okay, and which is for the 90% reliability, which means the 10% of the sample fail. Okay. Okay, so for the 90% in this area, it should be the okay sample. Okay, it should be the okay sample. Okay, so when we move this linear function parallel right shift, parallel right shift, which means our reliability will right shift also. Okay, always same distance regardless of the no this task load. I'm sorry. Okay. Similarly, so this linear function can also has the same distance left shift. Okay, say here. Let me change the color to yellow. Okay, at the same distance. Okay, so when this linear function right shift, right shift, right, right shift here, that's mean whose reliability becomes lower, right? Becomes lower. Okay, so similarly, when this linear function left shift, right? Left shift, that means its reliability increased. That means its OK sample increase in this area. Okay, in this area. Okay, therefore we can define this Weibull distribution whose reliability is a function R equals to exponential function. Okay, exponential function. Okay, and which can be obtained by experiment and provided by the battery manufacturers. Okay, provided by the battery manufacturers. Therefore, it's a manufacturer specs. Okay, so this x naught is the minimum value of x. The theta is characteristic parameters and b the shape parameters. Okay, I'm gonna briefly introduce this. So the reliability R for a Weibull distribution of life measure X is given by the exponential expression. So where the X naught is the guarantee or the minimum value of X. So what is X? It's a life. If you still remember for the last course, I introduced the dimensionless life cycle, right? So if you still remember the last, right? So here, right, we have the dimensionless rating life. Dimensionless rating life. Okay. So the X here represents the dimensionless rating life. Okay, where the X naught is the guarantee or the minimum value of the X. Minimum value of X. So X naught will be the lowest value of the cycles for which the first sample fell, which if using the Weibull distribution to feed all the data. Okay, and of course, it is not the real cycles for fail. Okay, we expect it by this Weibull distribution. Okay, and the characteristic parameter theta will be depend on the Weibull plot you obtain from the data, and it's also manufacturer's responsibility to provide. Okay, so when we run this Weibull distribution, we fit it, we'll get the characteristics data. Okay. Okay, so let's go back to Weibull for the reliability prediction. Okay, so we already know those parameters from the manufacturers, right? And what is X? That I mentioned previously, X is the dimensionless rating life, right? Which is a dimensionless rating life. Okay, it could be L over L10. X10 is the L10 over L10 equals to 1. It's dimensionless. And L10 represents the rating life, the manufacturer's number of cycle for test. Okay. Okay. So, when this XB is the you desire, what's the dimensionless life that you we can get this from, we can define the XB. Okay, we can define the XB equals to this term. Okay, we can define the XB in this term. Okay. Okay. So the XB that we define when the loading is C10. Okay, the C10. Okay, when loading is C10, we define the life, the dimensionless rating life is XB. Okay, it's XB. Okay, so we apply the C10, we get a rating life as XB. Okay, so the X10 equals to 1, right? Here, the XD is the desire dimensionless rating life. Okay, dimensionless rating life. Okay, so if we say this linear function here, the green line, whose reliability, desired reliability, okay, RD, desired reliability is 95%. So this linear function right shift can reach the linear function whose reliability is 90%. It's a it's RR. R is the rating life, and the RD is the desire reliability, and the rating reliability. Okay. Okay, so what we know is the desired load FD and the speed n and time expected to last, and the LD and expect a desired life LD. So we can convert it, right? We can convert it. Okay, we can convert it. Okay, and also we can define the dimensionless desired life equals to the LD over L10. Okay, so here for the LD not equal to, sorry, XD not equals to X10. Okay, not equal to X10. Okay, so similarly, we get from this linear relation, right? From this linear relation. Okay, so we already know this equation, right? So the desired life, desired load, desired life, dimensionless. Okay, and C10, the rating force, rating load, and the L10, right? Dimensionless, dimensionless rating life, right? Okay, so the RD, desired reliability, not equal to 90%, and the RR, the rated reliability in this case is 90%. Okay, in this case, it's 90%. Okay, so we can combine these two figures, this linear function and the white bolt distribution. Okay, we can convert it. So in this load and dimensions life, right? So this represents this linear function, right? And we put on one more z-axis, which is the reliability, right? Which is a reliability that can be represent, the reliability of the whiteboard distribution, right? Okay, so we can move this whiteboard distribution. We can shift it, right? We can shift it we can shift it. Okay, so we can shift this in to intercept with this linear function, right? This linear function equals to this linear function. So we can shift this y-ball distribution to find its intercept. Okay, so we can just move it, right? Okay, shift it. So this y-ball distribution have the intercept with the linear function whose rate reliability is 90%. Okay. Okay. It's 90%. Okay. So this linear function, 90% rate reliability, can left shift to get the linear function for desired reliability which is the 95%. Okay, which is 95%. Okay. Okay, based on C10, based on C10. So C10 is the rating force and FD is the desired force. Okay, it's the desired force. Okay. So step one, we find the XP. XP is the desired rating life, right? The desired rating life. Desired rating life. Okay. Desired rating life. So we can solve the XB, right? So whose reliability, desired reliability is 95%, right? It's 95%. Right? And we have this relation, right? For this linear function, right? For this linear function, okay? For this linear function. Okay, and A depends on the type of the bearing. In fact, it's based on the slope. Okay, it's based on the slope. Okay, it's based on the slope. Okay, so the first step, we get the XB, the desired rating life, dimensionless rating life. And the step two, we have this function, right? To figure out what this C10 is. What's the C10 is. Okay, what's the C10 is. Okay, so I have to correct what I mentioned previously. The XB is not the desired rating life, which is the rating life where the force is C10. Okay, when the force is C10. Okay, when the force is C10. Okay, this linear function is the desired reliability, right? But for this desired function, this linear line, this desired function, whose the reliability is 95%. So when we apply the forces C10, we get the dimensionless life XB, dimensionless life XB. Okay, so I have to correct what I said previously. Okay, so desire force, desire rating life, and the C10, and the XB, and XB. So what the purpose is to find what the C10 is. Okay, what is the C10 is. Okay, so we can rearrange this equation to find the C10, right? It's the C10. Okay, so therefore the C10 will equals to this. And we put a AF, which is the safety vector, or we say it's application vector. Okay, so we need to conservative to predict to the C10, what the C10 is. Therefore, we need the safety vector. We need a safety vector here. Okay. Okay, so one example. So we have the deep groove bearing. What is a C10 is? If the manufacturer give you some data. Okay, so the rating life is 10 to 6 cycles, x naught is 0.02, and theta minus x naught is 4.493, sorry, 4.439, and the B equal to 1.48. Okay, if the desire if the desired force is 250 pounds, and the ND, the RPN 350, and the life is 20,000, and the desired reliability is 99%, and the safety factor equal to 1.2. So what is a C10 is? What is a C10? So we can use this function, right? This equation. So we know the safety factor desired force, right? Desired force, and the XD can be found by the LD over L10, right? LD equals to RP, and we can convert it, right, into the revolution times 350 times the 20,000 times 60 divided by 10 to 6. So we get the XD, desired rating life, equals to 420, right? That's here. Okay, so, and then we can plug those parameters provide by the manufacturers here. Okay, so finally we get the C10 is 3,724 pounds. Therefore, we check the catalog. For this conditions, we have to find the C10 which is at least greater than this number. Okay, and remember it's a radial load only. Okay, it's a radial load only, and it's the deep groove. That means it's the no, it's a ball bearing, right? A equals to 3. A equals to 3. Okay, so this turns to XB right here. It's XB. Okay, so let's recap what we learned. Okay, so the reliability versus life. A constant load life major distribution is right skewed in the Y boat as a good candidate, defining the life major in dimensionless form as X equals to L over L10. The reliability is expressed with a Y boat distribution. So when we run experiment that I mentioned previously, we discovered this distribution is right skewed, and the Y boat distribution is a good candidate. Okay, so we run experiment for the bearings, and we figure out its probability distribution, okay, corresponding to low cycles, and then we figure out, wow, this distribution is similar to the Y boat distribution. Therefore, the Y boat distribution is a good candidate. Okay, so the Y boat distribution can be expressed as this term. Okay, so R is the reliability, X is the life dimensionless, okay, and X naught is the guarantee of minimum life of X, and the theta is the characteristic parameters for rolling contact bearing. This corresponds to 32.2%, so it's a percentage. Okay, it's a percentage of the X. Okay, and the B is a shape factor that control the skewness. For the rolling contact bearing, B is roughly equals to 1.2. Okay. Okay, so the whiteboard parameters X, naught, theta, and B are usually provided by the catalog. That's being provided by the manufacturers. And type values of whiteboard parameters are given on the page 601, okay, in our textbook. At a beginning of the end of the chapter problem. Okay, so if you have the textbook, okay, the Shikli's textbook, so you can just check it on this page. Okay, so it will give you, usually okay, some data present the manufacturers, okay, and its rating life. So for the manufacturer one, its rating life is 90 times 10 to 6. For the manufacturer two, whose rating life is 10 to 6 cycles, and whose X naught, okay. Okay, so we can briefly recap, summarize what we learned previously. So we have the rating life, right? And we can use that to figure out what is a C10 is, which has to apply a safety vector, right? Which have to apply the safety vector, okay? And this equation can be simplified slightly for a calculator entries. Now we can define the we know the log, right? 1 over RD, we can define it as the log 1 over 1 minus PF. What is the PF? PF is the probability for fail. Probability for failing. Okay? It's a probability for failing. Okay? So we can just approach this to 1 minus RD, the desired reliability. Okay? 1 minus the desired reliability. Okay, so this term can be simplified into this term, Okay? Well, it depends how you would like to calculate it. Okay, so combine. So I think I'm gonna leave this course next time, but I'm gonna briefly introduce what we are gonna teach next course. So for the previous course, we focus on the ball, deep groove bearing, okay, the ball bearing, okay, and whose the actual force can be neglect, or the actual force is very, very small, okay? But for most of time, we have to consider the axial and the radial load. Okay, we have to consider combined axial and the radial load. So if this bearing is subjecting to the axial force, how to evaluate its life? How to evaluate its life? Okay, and this force, no matter it's axial or radial force, are not the real force. Are not the real force. Okay, are not the real force. Okay, are not the real force. So I'm gonna leave this part to next time. Okay, for next time.